Hello. Today we're going to begin talking about Chapter 4, where we'll look at various types of chemical reactions, some that you're familiar with, others maybe not, but certainly in greater detail than probably what you've seen in your Introduction to Chemistry course. One reaction that may be familiar to you is the acid-base neutralization reaction. You may recall that this reaction produces water frequently. That isn't always going to be the case. In this photograph you see carbon dioxide being produced as the result of baking soda neutralizing vinegar. And although water is certainly produced, so is carbon dioxide. In the photograph in the lower left-hand corner you're seeing a precipitation reaction. Now, precipitation reactions are reactions where a solid is formed, and you can see the solid cloudy precipitate that's forming in that test tube. Over time, that precipitate would eventually settle like packed snow in the bottom of that test tube, but we're seeing its initial formation here. Frequently, precipitation will lead to cloudiness that will require quite a long period of time for proper settling to occur. Another reaction you probably have less experience with is the oxidation-reduction reaction. This type of reaction is responsible for the rusting of iron or steel to form iron oxide and rust. We'll look at this in much greater detail here later in the chapter. Also, an oxidation-reduction reaction, however, one that you're familiar with, is the combustion reaction. Combustion reactions typically produce heat and light. They are also oxidation-reduction reactions. Much of what we do in chemistry, and biology for that matter, involves the water molecule in some capacity or another. Typically, water is going to be a solvent in many of the cases that we're going to look at in this class, and certainly in the biological cases as well. Water is a unique molecule. Its very special properties make it possible for much of the chemistry around us to occur, both biologically and in more inorganic chemistry types of cases. And so what we're going to do is look very carefully at water and its structure in an attempt to understand exactly what makes it so special. Now, in the figure you see before you is the water molecule, and you should notice that there are two bonds involved in a water molecule. There's the bond between one hydrogen and the oxygen, and the other hydrogen and the oxygen. These bonds are covalent bonds. They are the OH covalent bonds. Covalent bonds, you should recall, involve sharing electrons. The hydrogen furnishes an electron, the oxygen furnishes an electron, and then the two happily share the electrons like the peanut butter in the sandwich, and that's what holds the molecule together. But what's also unique about the water molecule is that the shape isn't probably what you would have expected. If you had three atoms and they were connected together by two covalent bonds, why, you'd expect that this molecule that you've made would probably be straight. All of the atoms along a single line. But the water molecule shape is unique in that it's V-shaped. In some books, and later perhaps in the course, we'll refer to this as being angular or bent. But all three terms suggest the same shape for the water molecule, something other than being straight. This is important because its shape is responsible for many of its unique physical and chemical properties. Now, let's take a look more carefully at the bonds that hold the hydrogen to the oxygen. Focusing on the left-hand bond, you might think, oh, what a happy situation this is. Hydrogen has agreed to share its electron with oxygen. Oxygen has agreed to share an electron with hydrogen, and they live happily ever after, if you'll permit me to be so corny. But the truth is that in covalent bond situations, it's often the case that the sharing of the electrons in the bond isn't quite as even, or as uniform, or as equal as you might think. In fact, oxygen, the oxygen atom, has a unique characteristic in that it is quite attracted to the electrons. The oxygen atom is capable of attracting the electrons that you would think were in the OH covalent bond and attracting the electrons towards it. In fact, this goes on for both of the OH bonds. In either of the bonds, the oxygen attracts the electrons towards it. Okay, and these red arrows, called dipole moments, are indications of the direction that the electrons are being shifted within the molecule. Again, these covalent bonds are not a perfect sharing arrangement. Oxygen actually gets the electrons a greater share of the time than the hydrogen. Now, if this is true, then hydrogen is falling victim to oxygen. Well, if hydrogen loses custody of its electron, what happens to it? We have an uneven sharing of electrons, and oxygen has more pull for these electrons. To summarize, hydrogen loses the electron density to oxygen, and this has a very interesting effect. Here, what I've done is I've tried to suggest with color what happens to the oxygen and to the hydrogens. You see, the oxygen gets the electrons a greater share of the time, and therefore that end of the oxygen becomes negatively charged. That red fuzzy blob up there at the top is meant to suggest a greater electron density, that is, the presence of electrons more of the time in the case of oxygen. Now, who falls victim? Why, the hydrogens do. Those electrons had to come from someplace, and they came from the hydrogens. And what this means for the hydrogens is, without their electrons a good part of the time, why, they will have a partial positive charge. The Greek letter delta here is suggesting that although it's positively charged, we would say it's only a little bit. The electron taken from the hydrogen is not removed completely as it would be in an ionic bond. It is simply a redistribution or a slight tug on the part of the oxygen that nudges the electrons closer to the oxygen, making the oxygen slightly negative and the hydrogens slightly positive. In cases like this, where it's very clear that one end of the molecule is negatively charged and the other end of the molecule is positively charged in just that way, we often write an arrow or draw an arrow through the molecule that suggests that the negative end of the molecule is in the direction the arrow points, and the positive end of the molecule now, and in this case the positive end consists of both hydrogens, is where you see that little plus sign develop. So this dipole moment vector points in the direction of the negative end of the molecule, and then as a reminder, we've got that little positive end of the arrow suggesting the positive end of the molecule. Let's look at how water molecules can interact with other types of matter. In a more specific way, we'll look at how water is capable of acting as a solvent when sodium chloride is the solute. We'll be dissolving sodium chloride. And before we do that, here I've drawn a little schematic picture of what a sodium chloride crystal lattice would look like, microscopically, of course. And we see that we've got alternating sodium ions and chloride ions. What's important to note, though, is the force that's holding this crystal lattice together is the force that attracts one sodium ion to another chloride ion. It's an electrostatic attraction that exists between unlike charges, pluses and minuses. One sodium ion, one sodium cation, feels an attraction from 6 different directions, as there are 6 chlorides that are attracting it and keeping it locked into position. These attractive forces are very powerful. And in order to separate a sodium ion from the crystal lattice is going to take something unique, something special, a special set of circumstances. The crystal lattice is held together by very powerful electrostatic attractions. We'll bring in a couple of water molecules now. So we've just taken our solid crystal lattice and we've dropped it into a beaker of water. The water molecules, as we just discussed, are unique because they have negative and positive ends, and this is just what we need. Here I'm showing you 2 water molecules. Their orientation is quite important as they are pointing their negative end at the positive cation. Makes sense, doesn't it? After all, unlike charges attract, and so the water's negative end would be attracted to the sodium cation, the only thing that's positive and in that crystal lattice. And several of these water molecules can move in and be attracted to that sodium cation in just this way. And in the jostling about that occurs, it actually turns out that that sodium ion is broken free by these very strong attractions that it has for the water molecules, and it's liberated. It's pulled from the crystal lattice freely. And so we're seeing here the transition from being locked in the crystalline lattice on the left to being liberated and floating freely in the solution. Now there's more than just 2 water molecules floating around. Some molecules may instead go after the chloride ions, but these are going to be different now, aren't they? Here the chloride ion is a negatively charged species, And so, again, it makes sense that the positive ends of the water molecules are the ones that ought to orient themselves properly and exert an attraction for the chloride ion. They both water molecules, hook up on that chloride ion and will attempt to pull it from the crystal lattice. And of course, this goes on for other chloride ions as well as other sodium ions. And so it's a process that's going on, and we would be observing this as the dissolving of the salt occurs. Now, what happens once these sodium ions are plucked from the crystal lattice? Well, they're surrounded. They're surrounded by other water molecules. Typically, there are approximately 6 water molecules that surround a single sodium ion. Likewise, chloride ions are surrounded, but this time by water molecules with the positive ends facing the chloride ion. Chloride ions, being slightly smaller than sodium ions, require only about 4 water molecules around them altogether. The sodium ions and the chloride ions are no longer part of the crystal lattice. They're no longer locked in place the way they were. And consequently, because of the water molecules, the ions are now free to move. The sodium ions can move in any direction that they like. Okay, they'll be surrounded by water molecules that are sticking real close. But the sodium ions and the chloride ions are still insulated from one another by the water molecules that are getting between them, and they're free to move, unlike the sodiums and chlorides in the crystal lattice that were locked rigidly in place with only a little bit of vibration possible. How can we observe this experimentally? Well, this contraption here is just the experiment that we need. We've got a battery, a source of electricity. We've got a light bulb up there. And we've got a couple of electrodes that are placed in a beaker that we'll soon fill with some solution. Now, the idea here is that if there's a flow of electrons, or for that matter, any kind of charge, you've got electricity. Most people think of electricity as what comes out of the outlet, and certainly that is the form of electricity that we use. It's actually electrons that flow through the wires into our appliances and then back into the outlet again in a closed loop. Well, what we've got here isn't a closed circuit. That's the way the physicists like to refer to it. And that battery and the light will not light if it's set up just this way. What we need to do is complete the circuit. We can do that with a metal screwdriver. And if we do this, electrons will now flow through the wires, through the light bulb, through the screwdriver, assuming it's a conductor, and back into the battery. And as they go round and round through this complete circuit, the light bulb lights. So in principle, that's how this device works. If we place something that conducts charge between the 2 electrodes, and in this case it's been a screwdriver, not very interesting, we'll get to that in just a moment. If the electrons can flow, if the charge can flow through the circuit, then the light bulb lights. Okay, we can use our conductivity tester on something that's a little bit more interesting. And since we just finished talking about sodium chloride and how the sodium ions and the chloride ions are now free to move in the container, this is just the demonstration we need. The battery supplies charge, and the charge moves through the wires. Here the electrons are moving in a counterclockwise direction, and this produces negative charge and positive charge on the 2 electrodes that you see there. So these 2 electrodes that are immersed in this sodium chloride solution develop a charge as a result of the electrons that are flowing through the wire. This is where things get interesting, because in the beaker is sodium chloride, true, but not just ordinary sodium chloride, but sodium ions and chloride ions, sodium cations and chloride anions that are free to move in the solution. That means that the sodium ions, sensing the presence of the negative electrode, are going to head for the negative electrode. They will migrate to the negative electrode. After all, they're positively charged, and they'd be attracted to the negative electrode. Makes sense. The chloride ions are also free to move. And the chloride ions, being negatively charged, are going to move to the positive electrode. Again, unlike charges attract. Now, the fact that there has been sodium ion going to the left and chloride ion going to the right means that, technically, electricity has flowed. Electricity is the movement of charge. Electricity is not necessarily just the movement of electrons, and we have seen charge moving in this beaker, and we can rationalize it as simply the attraction that positives have for negatives. And so the result of all of this is that electricity will flow through the circuit and the light bulb will light. This is a good experiment to keep in mind. Simply what it tells us is that if the light bulb lights, then what is in the beaker must contain ions that are free to move. That's what it tells us. If the ions are dissociated and pulled apart and now no longer part of a crystalline lattice, but instead free to move within the beaker, if the light bulb lights, those ions are there and they're free to move, and they're what's responsible for conducting the charge and causing the electricity to flow. Let's take a look at a different situation. We've got the same experimental setup here. As you can see, a light bulb, battery, wires, and 2 electrodes, and the electrodes are negatively and positively charged in just the way they were before. But what is different is that in this case, the solute is not sodium chloride. The solute is C6H12O6. That's the chemical formula for glucose. Glucose is a monosaccharide sugar, and it's a building block in the composition of more complex sugars that string these glucose units together. Just a little bit of additional chemistry and biological application for you. What's important here, though, is that these glucose molecules I'm showing individually as C6H12O6 over and over and over again in that beaker. Now, the reason that's important, well, this is a molecular material. It's not made up of charged species. You don't see bits and pieces of pluses and minuses floating around in the beaker. When glucose dissolves in water, it starts out as a white crystalline substance and it dissolves in water. What happens is whole intact molecules of glucose break off. The smallest unit is a molecule that is C6H12O6, and it doesn't subdivide any further than that. What's also great is that the C6H12O6 has no positive, no negative end. It's a completely and entirely neutral molecule. Now, how is that going to affect the experiment? Well, remember that the sodiums went to the left and the chlorides went to the right because they had unlike charges, and that caused their migration to the oppositely charged electrode. But here we've got a molecular material, a molecular solute that has no charge. So which of the electrodes is it going to be attracted to? Neither. It doesn't really care that the left-hand electrode is negatively charged and the right-hand electrode is positively charged, and for that reason they don't go in either of these two directions. As there is nothing charged in the beaker and the solute hasn't helped things at all, no charge flows between the electrodes and no electricity flows through the circuit. This is to be compared to the sodium chloride example where we were dealing with the solution that formed from the dissolving of a sodium chloride ionic salt compound where ions were produced. Here, molecules are produced. They have no charge moves through the circuit, and no electricity flows through the circuit. Consequently, the light bulb doesn't light. Remember, when the light bulb lights, you've got ions present. When the light bulb doesn't light, there are no ions or charge carriers present in that beaker. Now, we've talked about solutions that conduct electricity and that don't conduct electricity. We have some descriptive terms that we use to describe these situations, and the first is a solution that conducts electricity really, really well is what we would call an electrolyte. That's one in which the ions are free to move. Weak electrolytes are solutions that don't conduct electricity very well. And non-electrolytes are solutions that don't conduct electricity at all. So according to these definitions, we've seen 2 of the 3 possibilities already in the slides that preceded this one. The sodium chloride solution was an electrolyte solution because that one lit the bulb. Lots of ions present, the bulb lights very strongly. If we had looked at an example for a weak electrolyte, why, the bulb would have glowed dimly in comparison to the sodium chloride electrolyte example. And in the case of our glucose dissolved in water, why, the bulb didn't light at all, and therefore it's a non-electrolyte. So this light bulb experiment not only tells us about ions, but also lets us attach labels to these different types of solutions. We have an entire range from electrolytes through the weak electrolytes, and then finally the non-electrolytes that don't conduct electricity at all. We've all heard the warnings, and they're good warnings. Never use an electrical appliance, like a hairdryer, when you've got a sink of water in front of you, or if you're standing in a puddle. Never use power tools around a swimming pool where the power tool might fall into the water. And why is it? Why are we so careful? We all know that water conducts electricity, and that if somebody happens to be in that swimming pool when an electrical appliance is dropped into the water, why that electricity will flow through the water and can kill the person swimming in the swimming pool. So these are good warnings, and you need to be aware of them. But the question that I'm going to ask is, why is water so conductive? Well, there are several reasons why water is so conductive. The first, we must be aware that if it's conductive, we can attribute this to the presence of ions. There have to be ions in that water in order for it to conduct electricity. Now, where are these ions coming from? Well, one place is simply as an impurity. The tap water that comes out of our faucets has traveled through miles of copper pipe and iron pipe, and it's been exposed to many minerals along the way, and consequently some of these minerals get dissolved to some extent, and these minerals appear dissolved in the water in an ionic form. So we may have some sodium ions and some calcium ions and some iron ions and perhaps some lead and cadmium, and who knows, hopefully in very low levels so as it's still healthy enough to drink. But the presence of these impurities, whatever they are, if they are charged, will cause the water to be more conductive. That's not the only place, though, or the only reason why water can conduct electricity. There's something going on behind the scenes, you see. Even if we had pure distilled water, the distilled water, by the way, that you use in the lab has been boiled, vaporized, and then recondensed in a distillery or a still, and most of these dissolved minerals have been removed. Not all, but it's been cleaned up significantly. And even still, ultra pure water will conduct electricity because of something very interesting going on behind the scenes. And here's what's going on. Water molecules are busy behind the scenes. If you have just two water molecules and they happen to collide with one another, well, what can happen, as is illustrated by this chemical reaction? The two water molecules would collide together, undergo a rearrangement, and then break apart again. But they break apart into hydronium ions, the ones in blue, the H3O+, and hydroxide ions, the OH-. The presence of these ions, the fact that they are produced as a result of just plain old ordinary water molecule collisions, is another reason for why the water conducts electricity. So there are really, just to summarize this, there are two reasons that water conducts electricity. You'll have dissolved impurities that, as long as they have a charge, positive or negative charge, they will contribute to the conductivity of the water. And even ultra-pure distilled water will conduct electricity to some extent because of the ions that are produced as the result of water molecules colliding with one another and the formation of hydronium ions and hydroxide ions. Here's that reaction again, and this time I've labeled it with the words forward reaction. When we speak of the forward reaction, we consider the reactants to be on the left and the products to be on the right. And this reaction, the collision between two neutral water molecules producing the hydronium and the hydroxide, is what we'll call the forward reaction. It's not the only reaction that can occur. Remember, in this beaker of water, there are collisions going on all of the time. Now think, you've got a hydronium positively charged cation and a hydroxide negatively charged anion. These are floating around out in solution. They're attracted to one another. And so it's quite likely that the blue hydronium and the red hydroxide, being attracted to one another, will probably react with one another given an opportunity. They're looking for each other, in other words. And what this means is that we can have a reverse reaction that occurs very quickly, as is often the case. The reverse reaction, we think of the H3O and the OH- as the reactants. The arrow now points to the left and shows us what we get. We get the original water molecules that we had to begin with. Both of these reactions are going on at the same time. Water molecules colliding, producing hydronium and hydroxide. Hydronium and hydroxide colliding, producing the water molecules. We frequently notate this, as I've shown you here in this third reaction, where we include both an arrow for the forward reaction and an arrow for the reverse reaction, both at the same time in the same chemical reaction. This is something that we call dynamic equilibrium. You might think that the ions never really have a chance to build up in the concentration to levels large enough to make the water conductive. But the truth is that they do. Yeah, hydronium and hydroxide very quickly convert back into water, but there are always enough H3O pluses and OH minuses floating around to make the water somewhat conductive. So dynamic equilibrium describes how reactants are turned into products, which are turned back into reactants again. The concentrations of the hydronium and hydroxide, well, they remain low because they're very quickly converting back into water. But they're still there with a significant concentration. And that concentration is why even ultra-pure water can be conductive. Let's turn our discussion of solutions that conduct electricity. Weak electrolytes, strong electrolytes, non-electrolytes. Let's look at acetic acid. I'm showing you some bottles of acetic acid in the upper right-hand corner. This is exactly how we get acetic acid in the laboratory when it's delivered. This is a special form of acetic acid known as glacial acetic acid. The chemical formula, CH3COOH, with an L down there. This is telling us that it's a liquid, of course, first and foremost, but it's also 100% acetic acid. Glacial acetic acid, those are the words for saying that you've got a liquid that is 100% acetic acid. Glacial acetic acid is a molecular liquid. This means that there are CH3COOH molecules floating around in a chaotic fashion in the bulk liquid, okay? And that these CH3COOHs never break up. They're molecules, after all. That would say that since these molecules do not break up into charged species, the glacial acetic acid is a non-electrolyte. There are no ions to conduct electricity. And if we were to take our electrical probes and dunk them into this liquid that is glacial acetic acid, the light bulb wouldn't light because there are no charge carriers to conduct electricity between the electrodes. This, however, can be changed. If you instead consider a solution of acetic acid, CH3COOH AQ, telling us that water is the solvent now, things change quite dramatically. When water is the solvent, then the solute is the molecular acetic acid. This solution, as it turns out, to be much more conductive than even pure water. Isn't that interesting? We add to pure water something that's not a great conductor but still conducts electricity a little bit. We add to that pure water something that doesn't conduct electricity at all, the glacial acetic acid, and what are we left with? Why, something that conducts electricity even better than the two of them. This is sort of strange, and one might ask, well, what's going on? Since the solution, the water glacial acetic acid solution conducts electricity even better than either of them did before, it's doing that because there must be more ions present, obviously. So where do these ions come from? This chemical reaction demonstrates where these ions come from. The glacial acetic acid molecule interacts with a water molecule. Now that they're both there, present, floating around, they can bump into one another, and the products are the H3O plus hydronium ion and the CH3COO negative acetate anion. Now, the names are not as important, although you certainly should know the name of the hydronium ion, the H3O+. The names are not as important as the fact that as a result of the reaction between acetic acid and water molecules, two things that have charge have just been produced. And the presence of these charged species are what gives the solution, the acetic acid solution, higher conductivity than either the water or the glacial acetic acid would have had to begin with. As a last note, notice that the arrows are double arrows again. This is another instance of dynamic equilibrium. These charged species, the hydronium ion and the acetate anion, are produced, but they're also attracted to one another, and so they would, in many cases, quickly recombine to reform the glacial acetic acid molecule and the water molecule. But enough of them are there with high enough concentration that the overall behavior of the solution is that of a stronger electrolyte, a solution that conducts electricity better than the distilled water or the glacial acetic acid would have before they were mixed. We're going to work out a quick example of how one determines the concentrations of ions from the molar solution concentration that might be found on the bottle label or something like that. In this particular example, we're looking to determine the concentration of copper and sulfate ions in 1.65 molar copper 1 sulfate. These kinds of calculations pop up frequently, and it's good to see one worked out. So there's the bottle on the left-hand side of the screen. It's been clearly marked as 1.65 molar, and now we'd like to know what the concentrations of the copper ions and the sulfate ions would be. The formula for copper 1 sulfate is Cu2SO4. If this is looking a little strange to you, you might want to go back and review your chemical nomenclature. Cu2SO4 breaks up in the presence of water into ions. It breaks up, and the two copper ions are released, individual, separated, with their own hydration shells, their own surround of water molecules, and then we also get a sulfate anion. And so the result of the copper sulfate crystal lattice breaking down would be 2 free-floating copper ions and 1 free-floating sulfate ion. So if we only had 1 mole of copper sulfate, then, and recall now that moles means counting numbers of things, then from 1 mole of intact copper sulfate formula units, we would have 2 moles of copper ions and 1 mole of sulfate ions. From this, we can actually get a conversion factor. We know that for every 1 mole of copper sulfate, we will always get 2 moles of copper ions, and this we can put together in a dimensional analysis. Here I've begun on the left-hand side with the original solution concentration. Recall that 1.65 molar means 1.65 moles of copper sulfate per 1 liter of solution, and that's how we start things off. Then we multiply by the conversion factor, which converts moles of copper sulfate, one of those, to 2 moles of copper ions, and I arrange things so that the moles of copper sulfate cancel out. The answer is 3.30 molar copper ions. If you go back and you think about this, it does make sense. The original solution concentration being 1.65 molar, but copper ions are present in twice the concentration because, after all, we get 2 copper ions for every 1 formula unit. So it stands to reason that the copper ion concentration should be double that of the formula unit concentration, since there is this 2-to-1 separation going on. We can do the same calculation, starting in exactly the same place, for the sulfate ions. Of course, the conversion factor now is different. We have 1.65 moles of copper sulfate per 1 liter of solution, as we did for the copper example, but now the conversion factor tells us that we only have 1 mole of sulfate ions for every 1 mole of formula units broken up, for every 1 mole of copper sulfate that breaks up. And so the concentration of the sulfate ions, because there is this 1-to-1 ratio, is exactly the same as the concentration that we have on the bottle, 1.65 molar sulfate ions. One of the last things we'll look at in this lesson will be precipitation reactions. And to demonstrate this, I've set up the following experiment. On the left, you see a beaker that's been filled with sodium carbonate solution. It's an aqueous solution where water is the solvent. On the right, the calcium chloride solution, again, utilizes water as the solvent. And soon, we'll combine them in the center beaker. At the moment, these two solutions are widely separated and, of course, in 2 entirely different beakers. When we pour them together, however, we get an interesting result, and that is the formation of a snowstorm or a precipitate, the cloudiness that one associates with a precipitation reaction. This was a solid not observed in either of the beakers to begin with, and so truly represents something chemical in nature. The solid forms. It consists of finely divided small particles that can sometimes appear as a cloudy mixture that would eventually, as shown here in this animation, settle to the bottom given enough time. Precipitation reactions like this are common, and we will be exploring these in more detail in just a moment. The solid does eventually settle to the bottom, and to the right there you can see another precipitation reaction, the same photograph from the opening slide, where the solid clearly visible in the test tube wait a long enough period of time, and that solid would eventually settle to the bottom and pack in. The next thing to do is to better understand the precipitation reaction, and better yet, identify the chemical identity of the precipitate that forms. Let's look at the details, beginning with the sodium carbonate beaker on the left. Now, sodium carbonate is a soluble salt, and this means that when sodium carbonate is placed into water, water being the solvent, it breaks up into 2 sodium ions and 1 carbonate ion. And so, even though on the bottle it may say Na2CO3AQ, meaning sodium carbonate aqueous, what we really understand is in that solution are 2 sodium ions freely floating and a carbonate ion freely floating. So the bottle label is often an abbreviation for what really is going on in the solution. This is true for the calcium chloride solution on the right-hand side as well. The bottle label may say CaCl2AQ on it, but what it really means is that we've got a calcium 2+ ion and 2 chloride ions floating around in that beaker of liquid, as well as the water that's there as the solvent. Now what we need to do is we need to consider, since we are going to pour these into the same beaker, we need to consider which of these ions might possibly get together, be paired up in such a way as to form the solid precipitate that we observed in the actual experiment. And we could consider, for example, the 2 ions, take one of the sodium ions and the calcium ion. They weren't together to begin with, but now they are since we poured them into the same beaker. Is it likely that they might combine in some way? And the answer to that question is no. Since they both have positive charges, the last thing they're going to want to do is approach one another and stick to one another, because we know that opposite charges repel. And so that the sodium ion and the calcium ion are actually going to stay far apart from one another and certainly cannot be associated with the product that forms. Well, how about the sodium ion and the chloride ion? Well, this is a more reasonable possibility. Since sodium ions are positive and chloride ions are negative, it only makes sense that these 2 things might actually come together, because after all, they're attracted to one another. However, we know from our past experience that NaCl dissolves in water. That is to say that it's soluble in water. And there's no reason to think that when sodiums and chlorides are placed into the same swimming pool, into the same water solvent, that they will behave in any different way. Sodium chloride is soluble in water, therefore we do not believe that the sodium chloride combination is a likely identity for the solid that forms. What other possibilities are there? Well, we could consider the carbonate pairing up with the calcium. We're thinking ahead here a little bit. At least we're picking ions that have opposite charges. This is a good thing, since opposite charged species will attract one another. We can consider the calcium and the carbonate, and indeed, these 2 pair up in a 1-to-1 ratio to form calcium carbonate, CaCO3, and that these 2 are the correct identity for the solid. The solid in this case that forms is calcium carbonate, the pairing of the positive calcium with the negative carbonate anion. Before continuing, let's agree on some definitions that we're going to be using here in Chapter 4 and throughout the semester. The first term is soluble, and the word soluble means that it's a solute that's going to dissolve in the solvent. We've seen examples of this. Solutes that are soluble in water include sodium chloride and sugar. Both of those will dissolve in great amounts in ordinary water. They would be considered soluble. Insoluble is just the opposite. This is a situation where the solid does not dissolve in the solvent, But we've got to be careful about this, because in chemistry and in science there is rarely an absolute. The truth is that everything dissolves to some extent. Everything. And so insoluble usually refers to something that doesn't dissolve in a solvent very much. But even something that's considered to be insoluble, even something that's considered not to dissolve at all, really does dissolve in water or in a solvent to some extent. Let's look at some examples of this, but first, one last definition. Solubility is really what gives us a measure of how much solute will dissolve. Solubility is the maximum amount of solute that will dissolve in a given amount of solvent. Here's an example that involves sodium chloride. This is a known fact about sodium chloride, that 6.14 moles of sodium chloride, now this is a lot of sodium chloride, even though it's a mole amount at this point, 6.14 moles of sodium chloride will dissolve in a liter of water. And at the end, you'll have a clear, colorless, very salty tasting solution of sodium chloride in water. What happens if you try to dissolve 6.15 or 6.30 moles of sodium chloride? What happens if you try to dissolve more than what the solubility limit permits you? Well, that extra salt sinks to the bottom of the container and it sits there, and it just refuses to dissolve. If we turn our sights instead now on a different solute, this is silver chloride. Silver chloride is considered by most to be an insoluble solid. You take a small amount of silver chloride, you dump it into a liter of water, and you watch it, and you stir it, and you try to break it up, and you cannot visibly see it dissolving very much. This is because the solubility of silver chloride is so low. In fact, only 0.0000135 moles of silver chloride will dissolve in that same liter of water that previously had dissolved 6.14 moles, 100,000 times more sodium chloride. So keep in mind, although silver chloride is considered by most to be an insoluble substance, the truth is that it does dissolve in water to some extent, just a very small amount. Now, how do we know what ions will form solid precipitates? And by the way, when a solid precipitate forms, it forms because it's insoluble. It's forming because it won't dissolve in water. So how do we know what combinations don't form solid precipitates? And the reverse of that, of course, is how do we know which combinations do form solid precipitates that won't dissolve? Well, there are solubility rules for this, and your book does a fine job of outlining them for you. We're going to just go through them quickly here. These come from your textbook. It's Table 4.1 on page 143. And the first solubility rule talks to us about those first group 1A ions, the lithiums, the sodiums, and the potassiums, and the ammoniums. They are all considered soluble. That is, when you see these things attached to counterpart anions, you can be assured that they're going to dissolve appreciably, that they would be a soluble salt. And so lithium, sodium, potassium, and ammonium, you can assume that those salts are going to dissolve. Nitrates and acetates, we mentioned acetates earlier, and perchlorates. Well, most perchlorates are soluble, so they would dissolve. Chlorides, bromides, and iodides are all soluble. But here's where we get into some exceptions. Usually, when hooked up with a chloride, a bromide, or an iodide, you are going to have something that dissolves in water, unless it's a silver hooked up with one of these three, a lead, a copper, or a mercurous. In these cases, what you will get is something that is going to form a solid. And so we need to be aware of these exceptions and what it means to be an exception. In this case, the chlorides, bromides, and iodides will dissolve unless they're hooked up with one of these four metal ions. Fluorides are also going to be soluble, but here's that exception again, unless the fluoride happens to be a lead fluoride or something from group 2A in the periodic table. Sulfates, why, they're soluble. Well, then there are the exceptions again. The exceptions are calcium, strontium, barium, silver, and lead. And so whenever you see sulfate paired up with one of these 5 ions, why, it's not going to dissolve and instead would form a solid precipitate. It would be insoluble. Well, let's look at the solubility rules again, this time from a different point of view. Let's look at the combinations that do form solid precipitates. Change in point of view. From table 4.1 in your book on page 143, one of the rules is that all common metal hydroxides are insoluble. Now, a hydroxide is an OH, and a metal could be, say, copper. And copper hydroxide, CuOH, would be an insoluble combination. That means that if you got the copper together with the hydroxide, they would pair up and they would form a solid that would sink to the bottom of the container and continue to be insoluble. But there are these pesky exceptions. If instead of a copper, let's say that we had a member from group 1A, the group 1A elements and the larger members of group 2A are exceptions to this rule. So take sodium, for example. If we take sodium from group 1A and pair it with hydroxide, normally it would be insoluble, but because it's an exception, the sodium hydroxide is soluble and will dissolve in water. Carbonates and phosphates, usually they're going to form an insoluble solid. Usually they will pair up and sink to the bottom of your beaker, unless they happen to get paired up with a member of group 1A or ammonium, NH4. In these two cases, they would not pair up to form something that would sink to the bottom of your beaker. The combination would be a soluble combination, and they would continue to be dissolved in the beaker. Sulfides are almost always insoluble. Hook something up with a sulfide, it usually sinks to the bottom of the beaker as an insoluble precipitate, unless it involves a group 1A element, a group 2A element, or ammonium. Again, there are these exceptions, and in this case, the exceptions would mean something that is soluble and would dissolve. The solubility rules, well, they're important. But what's most important is that you know how to use them and not that you have them memorized. And so for the upcoming exam and for exams to come where it's necessary to have solubility rule information, I will provide you with the solubility table that you see here on this slide. It's up to you to look over the solubility table and know how to use it. And probably the best way to get practice with the solubility table is to work lots and lots and lots of homework problems. And so print this particular slide out, have it with you, study it over, be familiar with it. You will see it again in the exam situation, but it's up to you to know how to use this to determine what pairs of anions and cations are soluble and what pairs of anions and cations are insoluble and would form a precipitate.